Hey, so welcome to my live stream. Today I'm going to be sharing, uh, I'll be going through a Medium article about building training architecture for self-improving AI agents. I want to read this with you and also implement the solution in the article. And let's see what will happen. So I'm sharing my screen. You can see this article. It's on Medium, and it's about agentic systems. So it says that like they rely on prompts to guide their actions, and the prompts are static. So we have to solve the problem of how the system learns, adapts, collaborates. Um, in the agentic architecture, subagents have different purposes. So we have to make these systems more effective by providing a training architecture that integrates reasoning, reward, and real-time feedback. And then it shows a typical training architecture for agentic systems. So all of this sounds quite reasonable. So we can move forward. So how does that thing look like? We have the agentic training architecture. So like my first question is, well, you have agents that are based on LLMs, and we know that LLMs can't be trained in real time. So probably we're going to train them by fine tuning or providing specific context and improving that context over time and seeing how it performs in different tasks. And we see here that we have evaluation by LLM judges, quantitative eval, performance eval, that we feed the fine-tuned sub-agents to this, and then we have trained data based on some knowledge, and we feed that into the architecture. We also feed tools in the architecture. It seems that this architecture is about some medical stuff, and we maybe the core of this is reinforcement learning algorithms that actually manage the training itself. So I'm not an AI engineer, like an ML engineer, so I'm probably a lot of things here are things I'll understand with you. Um, so yeah. So and then it goes to like several steps for the architecture. So first, we define the training foundation. So environment, initializing agent states, and aligning objectives of the agents with system goals. Then it's time to build the training pipeline. In this pipeline, multiple agents interact, learn in parallel, exchange knowledge. Then we're adding the reinforcement learning layer, and that uses some different algorithms like SFT, PPO, and contextual bandits. Probably we'll dive into these algorithms. Then we add observability and monitoring, so we can understand how the agents interact and learn. Design a dynamic reward system. So this gives feedbacks to the agents. Then it's a multi-phase training loop in which agents progress through different stages, from fine-tuning to full reinforcement-based adaptation, and then evaluate and refine the architecture. And then with this block, people are going to build a complete multi-agentic system combining reasoning, collaboration, and reinforcement learning to enable agents to adapt and improve through real-time feedback and rewards. Sounds interesting. And then they have the code of the system. And here is how we're going to proceed: setting up the foundation, then Society of Scientists using LangGraph, then building the reinforcement learning architecture, different reinforcement learning algorithms, then training loop, then performance evaluation, and then how the logic works. So let's see, it's pretty dense. It's like 70 minutes of reading. So, and I'm going to write code as we go. So the foundation is important, and we're going to install core libraries and dependencies, then configure API keys and Langsmith for observability. Then we're going to process the PubMed QA dataset, then design the central agent state, and then equipping agents with essential tools such as mock databases, Wife Web Search, and more. So let's start with the configuration. I'll open an editor here. So, and I will install UV and GraphViz. I'm on Mac, so I will install them with Brew. And let's see how the setup goes. I have to update some formula, but probably will manage that soon. Yeah, okay. We installed UV, and now we'll install GraphViz, Brew install. And then yeah, GraphViz is used to have visualization capabilities of one graph. Okay. And agent whitening with Vero and Unswat gives specific high performance training backends for our hierarchical strategy. Okay, so agent lightning is a trainer for AI agents. So it, as far as I know, it adds some trace sync logic inside the agent, so it can let it get feedback and improve. We have Vero, Volcano Engine Reinforcement Learning for LLMs. So this one is a training library for LLMs. Okay, that sounds cool. And Unswat, fine-tuning and reinforcement learning for LLMs. Okay, probably we'll base our work on this. Okay, so now we have to install all this. And until it installs, we can move forward. So sourcing the medical knowledge base. So yeah, we have to have training data, and we need that data so the agents can improve. And this is the pre-processing. So we have external knowledge, we have company medical database. We get this data, then we use Python plus the agents and convert it to structured docs from which we create training and evaluation data. And we don't rely on static hard-coded lists of facts, but we'll build a realistic research environment by using the PubMed QA dataset and the subset PQA1 specifically. PQAL, okay, and this is the dataset. Yeah, and it's not a machine learning engineer, so these things are something looking at for the first time. No idea what is it. I mean, obviously it's a data set for training, but I don't know how it looks like, what's it about, and so on. So it contains real biomedical questions, the original scientific abstracts that provide the necessary context, and final yes, no, maybe answer determined by this rich source of information for the agents and the ground truth for the reinforcement learning loop. Okay, so first we'll define the research task. And as I'll just start with a simple Python file, I guess. People are doing it in some kind of a co-op or something, but I'll just use it here and I'll copy paste things. So we have the research task. So the ID for the article, the goal, the abstract, and the expected decision. Okay. This is a blueprint using type dict. This returns something. It failed. And how did it fail? It says no module named NumPy. Okay, so I will add NumPy. uv pip install numpy, and then I will move forward with running this again. So yeah, we have the data set. Now we have to download it from Hugging Face, and that's strange. Okay, so I'll just use that and feed it inside quote code. It's time to launch this. No. Fails with. Let me copy paste it again. The following command, but it fails with. Let's see it fail. And until we see it fail, we'll, here it is. Fails with that. And let's see how quote code will fix it. SWOT is for CUDA GPU environments. Okay, maybe I won't be able to run most of this, but let's see. I will just skip on SWOT. Let's see what will happen. And now something else failed. VLM. Uh, and maybe I'll just go to Google Colab and open a notebook. New notebook. So so I'll start. I'll name it self warning agents, and I will start executing things here. I will put this to the left. And we're going to start over. Install system packages. Oh, no package UV, so probably I have to configure that. Let's see how I can use proper runtime. Menu runtime, change runtime, T4 GPU. Okay, T4 GPU, Python, latest. T4 GPU, okay. Save. And let's see what will happen now. Let's see why UV maybe UV is already here. Or what if I just set up Gravis? We would find it. Okay, Gravis was okay. Let's run the next one. Okay, it seems to have succeeded. Now let's create the research task. And then let's vote the data set. So this is how the whole data set. We download it from PubMed QA. We convert it to pandas data frames, then we go to each object and convert it to a research task. We do an 80-20 split for the training and the validation set, and then return the data set. Value error, what? Oh, okay, that's strange. So NumPy dtype size changed. Let's explain the error. We will use Gemini to help us debug stuff and see what happens here. And actually, meanwhile, I will also Google this because Gemini might be too slow. Try updating or reinstalling the NumPy package. It says, okay, let's do that. We'll run it. Yeah, probably NumPy isn't updated. That sounds good. Good job, Gemini. And let's see if we'll be able to load the dataset now. Successfully installed. It cleans up. And okay, let's restart the session. And okay, maybe now it can run and train the dataset. At least I don't see errors. Yeah, no. Maybe we should use PQA labeled. I guess the Medium article is a bit old. So I'll just use labeled PQA labeled and execute the function. Okay, now it says the above exception, key error contexts. So it says row of contexts. Row. How old is that article? It's pretty new. Why is it failing? We have, what did it say? Let's try with L again. First, maybe it's not labeled, but it's something else. Actually, I can use PQAL. So PubMed, we have PQAL and it's in data. View row. And each row has contexts, not context. Okay, so this should be, it's contexts. The above exception, key error contexts. Okay, if we don't have contexts, we'll just skip it. Let me remember a bit of Python, or actually, let's ask Gemini. Explain error. Let's see if Gemini will be smart enough to fix it. Before I started doing this Wi-Fi, I think I'll just copy paste some code and go through the article, and we'll have a self-learning agentic system. Cannot be found. The correct count should be context. Okay, let's see. I doubt that, but let's see what happens. I'll stop Gemini. So PK labeled. We want to run it. Let's see. PubMed ID. PQA labeled dataset. PubMed QA. I will go back and I will use PQAL, and yeah, we'll use that. We run it. And I think first of all, we should understand why. Okay. Yeah, it will use PK labeled. Let's see why it doesn't find the data set. Context. Maybe that should be PubMed ID. Let's see. Or actually we can. It's a bit. What do we have on each row? Let me print a row. See what do we have here? Pub ID, pub ID question context. Okay, so it's pub ID question and final decision. Okay, and I shouldn't have printed all the rows, but yeah, we have 1000 samples in the data set and we've split them into great. Yeah, so the 80-20 split is standard machine learning practice. Yeah, it gives us a large training set and a seed validation set to test how the agent performs. Okay, so we have the data. And now we want to inspect the sample, so we confirm the logic, and I really like that because I changed the code here, and I might have broken something. And I'll remove this print statement, And yeah, and now let's verify. So we have rich console. What are we doing? We create a temp table, we add some items, and then print the table. Okay, we have some data. Good. Sanity check. I'm not data scientist, but usually I'll just do proper tests here to make this work. But anyway, okay, so we have, yeah, and here they also have 1,000 samples, and they've split it in two, and yeah, and we have a similar table here that lists the data. Okay, so we've transformed the data into proper research tasks object. We use the research go, the question, as the initial prompt, and then expected decision is the ground truth for the reward signal. And then we have a knowledge to base the agents on. And now we have agent state. So we have the data and we have to design the nervous system for our agent society. This is the shared memory or state that will allow our diverse group of agents to collaborate, pass information, and build upon each other works. In one graph, this shared memory is managed by a central state object. Okay, so they say that a simple dictionary would be too fragile, and we use a nested hierarchical agent state using Python's type dict. So the agent state is as follows. It's shared between all the subagents. So we have a principal investigator, we have a review board, senior research, supervisor, junior research, and they probably use some tools or output some, have some outputs. This approach provides a machine-readable blueprint for our agent's entire cognitive processes. Each field in the state will represent a distinct stage of the research workflow, from the initial hypothesis generated by the junior researcher to the final peer-reviewed protocol. Okay, that's something cool. So the junior researcher creates hypotheses, then I guess the supervisor manages. There will be some flow of information going from the junior researcher to the principal investigator at the end. How are we going to do it? We'll define substates. So for each thingy here, so this is the state. So for each state, we'll architect the master state, and we'll add React. React is not React tool, but React Loop, React LLM, yeah, React prompting. So reasoning and acting, we instruct the agent to first reason about what they have to do and then act on it, and then inspect the action, reason again, act again. So we split the action from the decision on what to act on. So we will implement this as a basic here, I guess. Let's see. Okay, so first we define the data structure for the junior researcher. I'll add a new code snippet. So we have junior research, it's typed dict, they output a hypothesis with supporting papers and evidence and an agent name. Okay, sounds good. Then this is a blueprint for a hypothesis submission. So the junior researcher will output the hypothesis with supporting paper, yes, and then we have the experimental protocol. This is the output of the senior researcher. And it has to be detailed and actionable. So the protocol for the research contains title, it contains steps that we have to execute, safety concerns, and budget. Okay, sounds fun. I don't know how medical research is done, but I'll just trust the author on this one. And they say here that the protocol class formalizes the key components of a scientific experiment. So we require a title, a list of steps, safety concerns, and budget. And by that, we're instructing our senior researcher to think through the practical details of the proposal. This is far more valuable than a simple block of text and will be the basis for our final reward calculation. Good. So now we create the structure for the feedback from our review board. It's crucial for the revision loop. Okay, I really like how he starts with the data structures that are needed, and then probably will move towards the logic. The review decision is a critique of a given hypothesis. The use of literal is a key piece of engineering. It forces the review agents to make discrete choice, prove or revise, and to classify the severity. This way, we are allowing our LangGraph router to decide whether to send the protocol back for a major rewrite or a minor tweak. Okay, sounds good. And then we assemble them into agent state. Great, that's what I've been waiting for. We use the data structures and create an agent state. We will go through it piece by piece, I guess. So we have the entire cognitive architecture. The flow of information is as follows. So first, initial hypotheses are generated. We choose them we choose one of them as the selected hypothesis. So the junior researcher outputs hypothesis. Then the supervisor chooses one of the hypotheses. Then it's refined into an experimental protocol. Then it undergoes peer review, and then it has a final go or no go decision. So it's basically this flow here. Junior researcher outputs these hypotheses, the supervisor selects them, then we pass them to the senior research team, then to the review board to choose, to review the decision, and then we push that to the principal investigator to say go or no go. Okay, and then we have the final decision. Okay, so we have the agent state here. And the sender field, they say, is particularly important. It tracks which agent last acted, so two results can be sent back to it. Okay, so if the junior researcher acted last and the supervisor wants to improve the research, then it should send the information back to the junior researcher. And it says in a React, no, it's about using a tool, sorry. In a React loop, an agent decides to use a tool. After the tool runs, the system needs to know which agent to return the result to. Okay. By updating the sender field every time an agent acts, we create a clear return address, enabling this complex back and forth reasoning. Okay, that sounds great. This will be the memory for our system. And it seems like we can expand that on different agentic flows and use similar memory structures to devise other systems. Okay, so now we should build the scientific tooling system. So the agents have a sophisticated memory, but they need access to tools, of course. So we need to provide them with tools that search through PubMed, search through clinical trials, do protein database lookups, do gene ontology lookups, and will use LangGraph to orchestrate the agents and the tools they use. So now we are going to build the scientific toolkit for the society, and it will provide, the tools that I mentioned. So live web search, internal databases, and so on and so forth. So let's jump straight into the code. And by the way, for the people who watch, please let me know in the comments if it's interesting, if you have some questions. It's not a big audience, but I'd love to hear your thoughts. So we have the scientific toolkit. We use something called Tavily Search Client. Tavily is, we use it to search PubMed and clinicaltrials.gov. We mock a database for protein information and a second mock database for gene functions. Okay, so we'll mix Wive and mock tools to represent realistically real-world enterprise environments where agents need access to both public and private data sources. That's great. Let's try to run this because, we'll have to install this module, I guess. And let's ask Gemini to do it for us. Wow, that's quite stupid, Gemini. I asked you to install a module. Anyway, I'll just install the module. I will insert another code snippet and can I move it up? Yeah, I can. Okay, I will just move it up and do, let's see, LangChain community Tavily tools. No. Tavily docs, pip install LangChain Tavily. Okay, so we do uv pip install LangChain Tavily. And exclamation mark. Install. No? No. Why? LangChain. No, that's LangChain Tavily. Not found. LangChain community Tavily. Search API. No, Tavily search results. Okay. Tavily search results. No, where am I? Deprecated. No. Well, here's where my Python, or maybe I should just, let's see, Patrick Gomez. Here is LangChain community. What if I install LangChain community? Yeah, that was it. Great. We resolved that. Thank you, uh, Patrick Gomez. Now we should add this to PubMed search. So what it does, it just uses Tabili to do a query search in PubMed. Then we are going to create a tool for searching clinical trials. Okay, and do a bit of tabulation here. Again, it uses Tabili. Good, and now the mock database tools. Good. So that seems pretty simple. Yeah, so we just go into the protein database and search by war case names. Yeah, okay, great. And now we use simple dictionaries. Of course, these will contain SQL or API calls. And then let's instantiate the toolkit. We do this, and we can test it. What did it say? Did not find Tabili API key. Well, of course, Tabili API key. Let's see. Will it be for free? And I'll stop sharing for now, just for security reasons, and until I set up the API key. Or maybe, okay, I have an API key here. Have some credits. I copied it and okay, now I finally fixed my connection issues and I can continue streaming. I've set up the API key and now we can't find the Apple E4 field. Field require, let's see. We did gene ontology lookup, and we tried to search for it, and in the mockdb, oh, we initialized the scientific toolkit. So what's the issue? ApoE4, we do. Okay, we set up the env. Let's see what will Gemini think now. The gene symbol parameter is missing. Aha, okay, we should provide parameter. Okay, great, let's do that. So gene symbol and oh, that's strange. Let's see if Gemini will be able to debug this properly. Yeah, probably this article would have been way better if specified um, as a co-op notebook, because right now it's basically it doesn't have a good state inside, and I have to debug everything. But anyway, let's see what will Gemini find out. The error means Tuesday for the self. Okay, accept. Let's see what's this error missing. Required fields missing. What is missing? I love cryptic errors. We have self and gene symbol. Okay. Why don't we just do it like this? Okay, invoke, and we'll pass toolkit as self. Gene toolkit, gene ontology lookup, input. Gene symbol. It should be like that. Okay, I'll just feed this into an LLM and see what happens. So feeding it into quad. Here is quad's output as well, so you can see it. Okay. Okay, let's do it like this. And let's see what's the next error. Let's say, now I have this error. Okay, let's use the proper solution from Quad. Okay, thank you, Quad. It works. I won't. Let's just hope that this works properly in the whole setup. Great. So now we should design our society of scientists. So we have set up the tools. Now we should create the LangGraph system of subagents. We'll create a team of specialists with specific roles, and we'll assign to each roles and models with personas. We'll create agent runners. We'll architect the state graph, and we'll visualize the architecture. Great, that sounds fun. So building multi-agentic scientific system. A key principle is that not all tasks are created equal. So we shouldn't use a single massive model for every job. Instead, we should assign different open source models from Hugging Face to different roles. Totally agree with that. Right model for the right job approach is a cornerstone of building production-grade, cost-effective agentic systems. Okay, so we have several junior researchers based on QuenSmall. We have geneticists, pharmacologists, and neurologists. We have supervisor based on Quen. We have senior researcher and placeholder. Probably this model here hasn't been selected. We have protocol designer with Quen. Then we have peer reviewer and safety officer with Mixtral, and then we have principal investigator with Mixtral. So fast small model for creative brainstorming, placeholder for the more powerful model that will fine tune with PPO for the senior researcher, and a Mixtral model for the critical review tasks. Okay, wonderful. Let's do that. Let's create them and see. So the junior researcher is using Quen. Probably I'll have to run Ollama server. Let's see. Senior researcher, we should find the proper model and Mixtral here. Good, probably this will error. Okay, it defined them. But probably if I try to run this, it will fail because I haven't run Ollama. The respective, let's see. I'll configure Ollama soon, but first we have now defined our research team hardware. Quen to 1.5 billion. To the junior, we enable fast, parallel, and low-cost ideation. Senior researcher is a logical placeholder. Agent whitening, we will accept calls to this model name and route them to our PPO trained model so we can update its policy, and then Mixtral for the rest. Next, we need a standard way to combine a model, a system prompt, and a set of tools into an agent. We'll create a factory function for that. Great. What does it do? It creates a prompt and binds the tools. Great. And yeah, and specific prompts for each agent. Let's do that. Okay. And now we have the cast of AI scientists. And we want them all to respond with specific JSONs. And then we want to create state graph with React logic. And this is the state. We start, the junior team conducts research, the senior team creates protocol, review board checks the plan, and updates the protocol. If it looks good, then the principal investigator gives okay. It's not a linear pipeline like here. And we have feedback loops for revision and a robust mechanism for tool use. We'll build the agent nodes, React style to use multi-level revision loop and visualize the graph. Okay. So now we are going to build the agent node itself. What does it do? Just execute it. It creates an agent, and we load the and we update the state based on the agent state we defined earlier. Okay, so when an agent runs, we'll log its activity, update the safety counter, and most importantly, update the sender. And the sender, we know, will enable the React logic. And this will ensure that the JSON feedback is parsed and placed in the respective fields. And now we'll define the React loop itself. We get the last message. If it has no tool calls, then we should go to the next agent. If we've done the maximum number of turns, we should we should stop. Otherwise, we should choose a tool. Agent state is not defined. Of course, it is defined. It's not. Okay, let's run agent state to define it. Okay. And then we need a router. So if we are on the tool stage, we should use the correct sender. And now is what happens after review. So we get the peer review and the safety review. If we've gone out of turns, we go to the principal investigator to make a decision. If a review has a critical severity, so we should go back to something called hypothesis refiner. If it's major, we should go to protocol designer. If it's minor, then we should go to make a final decision. It inspects the severity, and yeah, so this route here will, so on critical, we'll go to the hypothesis refiner tool. Basically here, we'll jump back to the junior team. On major, we'll go to the senior team to change the protocol. Otherwise, we'll move forward. And then we should build the graph and visualize it. Let's see what will happen here. Install PyGraph viz to, okay. We'll install PyGraph viz uv pip install PyGraph viz to move that up the chain and install. Okay, Gravis as well. Probably I haven't installed the modules here. No, they're installed. Okay, I will look into that on the next session. So this is how the graph will look like. We have the junior researchers. All of them use some tools and execute them. And once they have something, they pass it to the senior researchers. So hypothesis refiner and protocol designer. Then this is passed to the reviewers. And if everything's okay, we go to principal investigator. So uh, basically, we'll continue with that uh, during the next session. Thank you.